Hello, and welcome to The Most Significant Bit, a podcast that explores the connections between engineering, technology, humanities, and the arts. I'm Vincent, and today we're discussing how nature has impacted aircraft wing shape design. In this episode, we will discuss how elements in nature have impacted the design of aircraft wing shapes. We will start with a brief look of the history of flight and a cursory look at the physics of flight, then examine how shapes found in nature changed the way that we look at wing shapes, and examine how this impacts flight today. Humans have been trying to fly for much of recorded history, with one of the most early notable examples being the myth of Icarus. While Icarus, of course, crashed, for a long while after him, people tried making their own wings like birds or bats and mimicking their flight. This is, of course, an example of early biomimicry in engineering. While we know today that affixing feathers to a wooden frame with wax and trying to flap like a bird or a bat would not allow a man to fly, this is actually a good example of what held humanity back from flight for millennia. It's an intuitive thought process to try to mimic the mechanisms of other things that fly. After all, if we know that birds fly with their big feathered wings, why wouldn't we try that? Unfortunately, this line of thought would become the philosophical wall that would prevent human flight rather than the engineering one. Humans simply can't fly the same way that birds can due to our biology and physics, which were poorly understood at the time. We wouldn't see successful unpowered flight or gliders until the 1800s, which laid the groundwork for modern flight, and we wouldn't see successful powered flights until the early 1900s. Despite huge advancements in the field, the physics of flight were still somewhat poorly understood, and many early aircraft were made with boxy rectangular wings, which were cutting edge at the time, but today we recognize as somewhat primitive and very inefficient. In the decades following the early Wright flyers, we came to understand much more about the physics of flight and the engineering that went into a good aircraft. A term that began to be used in flight physics is the Oswald efficiency number, represented by lowercase e naught. This, in simple terms, represents how efficiently an aircraft produces lift while minimizing drag. These numbers genuinely exist on a range from 0 to 1. You could estimate a thrown brick to be a zero point 0.3, the early rectangular winged aircraft like biplanes scoring a zero point 0.6, a Boeing 737 around a zero point 0.8, and complex, highly efficient elliptical wings like on Supermarine Spitfire from World War II, very close to a 1, being a perfect score. Elliptical wings were considered to be the best possible wing shape at the time, according to the math. But eventually, scientists and engineers realized that their ideal answer was not the same shape as the ones that birds and fish fins had, either meaning that nature spent millions of years evolving to the wrong solution, or the physicists got it wrong. After some experimentation, it did turn out that nature was right, as it typically is. Certain wings on birds and fish were able to score an Oswald efficiency number of 1.05, which may not sound significant, but this means that they were 5% more efficient than the math thought they should be. As it turns out, analysis of nature's wings gave us a deeper insight into drag models and showed us some neat ways that animals were combating drag, like fish fins having certain surfaces with help with flow, and bird wings having certain shapes to help with vortexes in the wind, minimizing drag and increasing lift. While this is a really cool advancement, its application today unfortunately lies at a crossroads of cost and manufacturing difficulty. The elliptical wings of Spitfires mentioned earlier were very difficult and expensive to make as it was, and the complex shapes of the wings that we see on birds like eagles would be even more expensive and difficult to produce. Not only that, but these highly efficient wing shapes get less and less important at high speeds, where material limitations become more pronounced, and relatively inefficient swept wings, like those seen on modern passenger jets and fighters, become nearly required. These designs are still used, just in specific roles or high performance aircraft, such as highly efficient glider aircraft, where prioritizing lift instead of drag is very important. It is somewhat ironic that humans trying to mimic nature's flight at first kept us out of the sky, but later gave us the keys to taking full advantage of it. Today, we covered the history of early human flight, how birds helped us design better aircraft, and how our designs have evolved over the decades. There are so many ways nature has helped us design a better tomorrow, and it continues to inspire us at every step of the way. I hope you enjoyed hearing about this one. Thank you for listening.